Hi everybody and welcome to another JASP tutorial video. Today we are going to talk about how to do a one sample t-test. And as always with this current tutorial series, I am using the JASP 0.10 preview release version in order to talk about one sample t-tests among other t-tests. I'm going to use data file that we've been using for previous videos. This is a data set that I have had for about 5 years now, and it's not the most useful data set for one sample t-tests, but we're just going to fudge it a little bit. I'm going to use a variable from here that we can use to test this one sample t-test. So one sample t-tests are fairly straightforward. You go to t-tests, one sample t-tests. Now, one sample t-tests essentially give you one piece of output, and then we can add some additional statistics to the mix and do an assumption check for our t-test. Now, the one sample t-test is based on a z-test where we have a mu value, which is going to be our test value, but with a z-test, we also know the population sigma, or standard deviation. Okay, so with the one sample t-test, we have the population mu, or mean, but we don't have the standard deviation. So I'm going to go ahead and uncheck that because we are going to deal with the one sample t-test. So I think it's really cool that JASP added the z-test here. So if you have stats homework that you need to run a check on your algebra, running the z-test by hand, you can then just plug in those values here for the z-test and find out whether or not your math was right or if you made a calculation error. It's always rounding too early. Okay, so we are going to do the one sample t-test, and the variable that I've chosen for this particular example is the accuracy score for incongruent or conflicting problem types in the lawyer-engineer problem. So I have a number of participants who solved, I think, 6 conflict or incongruent problems, and so they all ended up with an average accuracy score across those 6. Now, so you can put multiple variables in here. They all have to be of the scale type, so none of these work. They all have to be one of these, so with the ruler icon. But you can put them all in here. The only problem is that they all have to have the same test value. So you're not going to put in variables here to run multiple tests that you get the results over here if they all have different test values, a different population mean that you're testing against. We could also talk about the Wilcoxon signed rank test. This is a non-parametric test, so it has less power to detect an effect if it's there, and this would be used for if you violate assumptions of normality, which I'll show you in just a second. You may have even done the normality check before by using descriptives, but here you can just run it all at once. Now, if you violate an assumption for the t-test, which is a parametric test, you might want to throw the Wilcoxon signed rank test in there. Okay, so I'm going to go ahead and check that box. Here I'm going to change the test value. This is going to be a bit arbitrary for the actual example here, because there isn't a population value for incongruent accuracy scores, but you do see quite a bit that it's around 0.3 in studies over the past decade or more. So I just thought 0.3 would work. And as soon as I click away from the box, you can see that the results shifted to include the 0.3 estimate. And the statistic and the Wilcoxon statistic changed, and we have our degrees of freedom and our p-value, so the probability value for that particular variable and that particular test. I'm going to go ahead and I'm going to skip alternative hypothesis for just 1 second and click the assumption check for normality. So this is extremely important. You need to have a normally distributed sample in order to use the parametric student's t-test. So if we violate normality, then we have to go to a non-parametric test, which would be Wilcoxon. Now, on the assumption check screen here, it comes up with the Shapiro-Wilk test of normality. We talked about the Shapiro-Wilk test in a previous episode when we went over descriptives. So it gives you a W value, and then it gives you a P value for deviation away from a normal curve. So, generally speaking, and this is what I learned in both undergrad and grad school, please correct me if I am wrong, but you want to set a conservative p-value for your tests, for your assumption checks. So it's not the same alpha value as this p-value, your test statistic for that mean. It's a different alpha value, and you can generally choose something along the lines of 0.01, 0.001. In this case, as you can see here, the p-value is less than even the most conservative 0.001, which I don't suggest going any lower than that. So it appears here, and as you can see from the note, that there is a deviation from normality in the distribution for this variable. So we have an issue here where student t-test might not actually be appropriate. This is partially the reason why I chose this variable, so we could actually go through this part of the example, because otherwise, normality is good. We can check that. But here we have an issue, and so we have to make the determination whether or not we should be using Wilcoxon or student t. Now, you can see that even without anything presented, both of these test statistic probability values are less than 0.001, which is the level of precision that you don't really want to go lower than. So we can make the argument that regardless of which test we use and which statistic we report, although it's more appropriate to report Wilcoxon in this case, that the mean for this particular sample is different from the population mean of 0.30. Now that brings me back to the alternative hypothesis selection here. You can see that these are radio buttons. You can only have one of these applicable at any given time. They're not a checkbox. You can't just have them all selected. So you choose one or the other or the other. And these represent the kinds of directional tests that you do for this variable, for this test. So the default is not equal to test value. That just means that we're saying our alternative hypothesis, or H1, is just different in either direction, plus or minus, from the null hypothesis, or H0. And that's the default that null hypothesis statistical testing, NHST, instructors use all over the board. But we can also change that to a one-tailed test. The not equal to sign is considered a two-tailed test. So we're looking at the tails, both tails, the positive and negative tails of the t-distribution to find out whether or not our mean is different than the test value mean. But we can also just put all of our eggs into one side or the other, the positive side or the negative side tail. And so these two, the less than, or greater than or less than signage choices, we'll put all of our alpha into the positive or the negative side tail of the t-distribution. We choose these when we have a directional hypothesis, when we say that, okay, well, on this particular variable, I think people are going to do better because I've made some sort of change to the way that the problems have been presented in the past. So I think this change that I'm going to make is for the better, so they're going to get better. So I'm going to go ahead and choose that one. And you can see then it changes our test statistic. The assumption check doesn't change because the changing the alternative hypothesis doesn't change the distribution. So I just want to make that clear. And you can see that not much has changed. I can go back and forth and you can take a look, and there's actually no change whatsoever except for the note. Everything else is different. And that's because, as you'll see in a little while, when I put up the descriptive statistics, it is greater than. So it doesn't change, and you can see the p-values are well far in the tail of the t-distribution. I can also, just for the sake of argument, choose the less than. So this is saying that, oh, the change that I made to this problem type, these conflict problems, are going to make people do worse than the population mean. They're going to do so much poorer. And so that's the directional hypothesis. I'm going to put all of my eggs in the less than bucket. And you can see here, again, the test statistic doesn't actually change. But here's the thing with this test value not changing when we look at 0.3 versus 0.65, or 0.56, excuse me. When I load up the descriptive statistics, the mean of the actual sample is not less than 0.30, it is greater than. So this would be an inappropriate test to choose, even though it didn't change any statistics here in the one sample t table. And so we don't want to actually use that here. So I'm going to go ahead and just, before we continue, I'm going to go ahead and click it back to not equal to. So here you can see we're back to these statistics. Okay. Additional statistics that we can add to our table. Our table's going to get actually quite bigger. It's going to go past the screen here, so you won't be able to see. I'm going to go ahead and choose the location parameter. For one sample t-test, the location parameter is the mean difference d. Okay, so the difference between your test value, your population mean, and your sample mean. So that's just one minus the other, and it's the absolute value of it in this table. So you can go ahead and just click that, and one minus the other. Doesn't matter which one's first, which one's second. For the Wilcoxon test, you can see the number is slightly different, and that is because it is given by the Hodges-Liebman estimate. I will be honest and say I don't know exactly what that is. I think it's an adjustment of the means versus the test values. We can go ahead and put in the confidence interval for that location parameter. So I'm going to slide the bar over here, and here we have the 95% confidence interval, and both have a lower and upper estimate for that location parameter. Okay, and that just means that we have some uncertainty about the mean difference. Now the effect size we can add here. JASP for t-tests uses Cohen's d, as you can see. For student t-tests, the effect size is Cohen's d. For the Wilcoxon test, this is the matched rank biserial correlation. So it is an ordinal biserial correlation. So it's a non-parametric test. So it's that value there versus a Cohen's d of 0.825. We can also go ahead and add in the 95% confidence interval for the effect size. And so you can see here that we also have some uncertainty about where that effect size is for both student T and Wilcoxon. So those are the ranges for that effect size. Now, as you can see here, if you're familiar with Cohen's d, so we have the test statistic over here, 0.655, degrees of freedom of 62 because there are 63 respondents. So 63 respondents, n minus 1 is 62, and a p-value of less than 0.001. So quite a small probability value for that. And so correspondingly, it looks like we have a very large effect. If you're familiar with Cohen's d, again, 0.80 is a large effect for this particular output. So the 0.55 mean for the sample is quite different from the population mean of 0.30. Okay. So I'm going to go ahead and add descriptives. This adds a descriptive table. It gives you basic descriptives for your variable or variables, depending on how many you have in this box there. So there are 63, as I said, 63 people. Mean, there's the mean that I've been talking about, 0.556 or 0.56, standard deviation of 0.31, and a standard error of the mean of 0.039. So basic descriptives for the test statistic. We can also get our descriptive plot, and you can resize this to make it a little bit smaller. One of the things that JASP does is it automatically chooses the scale and puts the plot there. Now, it puts in the confidence interval bars, so these are not standard error bars. These are 95% confidence interval bars. Okay. And I'm going to go ahead and skip the Vovok-Selke maximum p ratio. I don't know that, so I'm not going to talk about it. But it is an option if you wanted to compare your alternate hypotheses to your null hypotheses. You can plop that in there, and it will add a line to your one sample t-test table. Finally, you can exclude cases for missing values. T-tests do not like missing values. They don't work. So you have to exclude missing values. So you can exclude cases, analysis by analysis. That is if you have multiple variables here. Or you can just exclude cases listwise, which means that if a particular row has a single missing cell, so let's say you have multiple variables here, but only one of the values is missing, well, all of that row is deleted for all of the tests. Otherwise, you can exclude cases analysis by analysis if you want to go through test by test, and it only deletes missing values for that particular variable in this box here, rather than the entire row from the analysis. So that choice is open to you, and you can go ahead and export this. Utilize the information here to present what the data look like. I'm going to go ahead and put a text box in the video. It should be appearing now, which shows you the APA notation for this particular t-test. I'll put it in some white space next to the assumption check Yeah, that sounds about right. It should be, you should be able to see it there in all of its APA notation glory. Well, that'll do it for this tutorial. Please leave your comments and feedback down below. And thank you for watching. Bye-bye.